All right, reading responses on the section that we're doing today on interpreting the definite integral. Most people seem to feel pretty good about just how do you deal with an interpretation of a definite integral? How do you put it in practical terms? The one place where folks did not seem to feel very solid was how that interpretation was put into play when there was a graph of the rate of change function, specifically example 3, where you had a velocity and it's like, oh, this is the point on the velocity curve where the person is furthest away from home. Again, a lot of people had questions about that. So we will get a look at a graphical example just to make sure that you're feeling okay with that. But again, we're also going to be doing calculations and interpretations from tables and from formulas, things that you've been doing up to this point, and I think that you've been feeling pretty good about. All right, so let me get the whiteboard going here. Just a second. There we go. All right. If f of x is a rate of change of a quantity, then we interpret the definite integral from a to b of f of x dx as the total change in the quantity between x equals a and x equals b. So something like this. Let's say that Wt is the rate at which water is leaking from a tank. In gallons per minute. And T is being measured, therefore, in minutes. Now, using the format that we have up here, this should be the total change in the quantity. This is really the big issue is, what are the units that we're working with? Something that I find really helpful for keeping track of the units.
I'm gonna go do the stuff.
Hi, somebody's not muted, so I can hear what's going on in your household. Thank you. We're told in this problem that Wt is measuring in gallons per minute, and we're also told that time is being measured in minutes. So when you see that little dt, remember we interpret that as the change in time. When we were doing rectangles, that would be the width of each one of those rectangles. So this is minutes. Now we're taking gallons per minute and multiplying them by minutes, and so that those minutes are going to cancel, and that gives you the unit of your definite integral. That is our quantity. So this is telling us the total change in gallons between t equals 3 minutes and t equals 4 minutes. Now that's kind of an awkward phrasing. The total change in gallons between t equals 3 minutes and t equals 4 minutes. Really, we would just want to say, hey, how much water leaked out of this tank in the 4th minute? Let's say between t equals 3 and t equals 4. But it's good to have a template that you can work from, because then once you put it in that sometimes occasionally awkward template, then you can translate it into words that make a little bit more sense. But again, this ability to see the dt itself as having units that cancel with the denominator units of your rate of change function, that's what gets you to your quantity, because f of x is a rate of change of a quantity, and we're getting just the total change in the quantity here. So this would be the total change in gallons between t equals 3 and t equals 4 minutes. Okay, now let's see what this looks like if your rate of change function was given as a graph. I'd like to erase this if I may. We good? Okay, cool. All right. So this was the part I think that gave people the hardest time, was something like this. Let's take a rough graph. And I'll have this be time in seconds, and this is velocity in meters per second. So, all right, now one of the things that can be a little off-putting on a graph like this is the idea that velocity could ever be negative. Like, what would it mean to have a velocity of -2 meters per second? And yet that's exactly what's happening here at 4 seconds. Velocity does have a direction. Like if we talked about a velocity of +2 meters per second, we could say that the object is going to the right. And so -2 meters per second would be the object going to the left. You could do a different direction where positive velocity means the object is going up. It's away from the surface of the Earth, and the negative velocity would mean it's coming down back towards the surface of the Earth. Or you could have a positive velocity saying that we are going away from home, and a negative velocity saying that we are going towards home. So let's do that. Away from home. And if you turn back around, then you're going toward home. So we can make this a little bit more consistent with that example 3. A lot of people seem surprised by the idea that you're actually furthest away from home right here, because it feels like velocity is 0 and that seems contradictory. Well, we can talk about it at an intuitive level, but I actually want to start first in terms of just calculating some numbers. If I were to do the following. Okay, first off, let's talk about the units. This is in meters per second, whereas this is in seconds. The seconds and the seconds cancel, so the unit of this accumulation is going to be meters. So this is the total change in meters. From t equals 0 to t equals 1. In other words, how far did this object travel away from home in the first second? Well, we can actually get a number here. It's the area under that curve. That area happens to be a triangle. So, how big is that triangle?
1.
So, and what is the unit of that one? 1 what?
1 meter.
Right, exactly. Our units are meters. So change of 1 meter from t equals 0 to t equals 1. So you went 1 meter away from home at that point. If we went from, say, 0 to 3, our units are still meters, and so we're still adding on some extra. All right, I want to evaluate now between 0 and 3. Now we've already evaluated between 0 and 1. That had an area of 1. And now I'm going to evaluate between 2 and 3. What's the area of that of the extra triangle that we just added on there?
2.
Yep, so put those together. We end up a total distance traveled there of 3 meters. So as long as your velocity function is above the x-axis, then you're going to be accumulating additional meters. That's why at this point, you're the furthest possible away from home, because you've added on as much positive velocity, as much positive rate of change as you can. Now, at this point, we are going to end up turning back around. Let's see, we'll go from 0 to 4 v of t dt. Actually, I'm going to go from 0 to 5. Let's do the whole thing. Well, there's the 0 to 3 v of t dt, and there's the 3 to 2 v of t dt. Now, we already calculated this as being 3 meters, so we'll just replace this with a 3. I wanted to have that from 3 to 5. My apologies. Now we're looking at this region here from 3 to 5. What's the area of that triangle?
2.
Yes, and it's also negative. It's below the axis, so we're not adding on additional distance traveled. We're going to be taking that distance traveled away. And we get ourselves at between 0 and 5 meters. We are now, again, think about the term total change. If 0 is our home position, then we've had a total change of 1 meter away from home at this point. Really, all that's saying is that we went back, we went forth, but where we landed was 1 meter away from where we started. Now, that's different than this one right here, because this is saying, oh, just in that first second, I moved 1 meter away from home, and that was it. There was no back and forth. But over the entire 5 seconds, the total change in my position, accounting for going forwards and backwards, left me at 1 meter away from home from where I started. That is my total change in my velocity. Now, again, if it had turned out that the red area and the blue area were equal in measure, then you would have been able to claim legitimately, it's like, I went away, came back home, the total change is 0, but some things happened in between. As soon as we switch over though from positive accumulation of velocity, meaning that we're moving away from home, to negative accumulation of velocity, meaning we're moving back toward home, then we're going to start reducing our total. And that's what we're seeing here. Now, I want to show, because someone did ask about, hey, how do you do this with Desmos? Let's, kind of show how this would work with Desmos. One like this, you would have to be given a graph from which to calculate. And I do think that one of the problems with the graphical ones is that there's so much guesswork about the value of the function. So I'm going to try to be as cautious as I can to give you graphs that look like this in nature, because you can calculate the exact area of these triangular and rectangular regions. That's going to make it a lot easier. But let's get a look at one where you can use Desmos to do the work for you. All right, I'd like to erase this. All right. A hot cup of coffee, let's say 90 degrees Celsius, is put in a cool room. Say 20 degrees Celsius. And the coffee's temperature is changing at a rate of, oh, no, sorry. R of t is equal to -7 times 0.9 to the t power degrees per minute. All right, let's interpret this. Okay, let's start with the 0 and the 10. 0 what and 10 what? What are the units for the 0 and the 10?
Minutes.
Yes, so we are looking over a 10-minute interval here, and not just any 10-minute interval, the first 10-minute interval. Now, there's also the units of R of t. Those are our degrees per minute. And our t, which is in minutes, those minutes end up canceling, and that means that this whole summation is going to give us something in degrees. Somebody try putting it into words what this definite integral would calculate.
The total amount of change in temperature during the first 10 minutes of the coffee cooling.
Yep, it's like, how much of a temperature loss do we have in the coffee? How much does the coffee cool down? What are the units by which we're measuring that?
Degrees per minute.
Actually, it's just degrees. It's the total change in degrees between t equals 0 minutes and t equals 10 minutes. Once we've done that cancellation, our answer is just going to be in degrees. How many degrees did the coffee temperature go down? So let's put that here. How many degrees did the coffee cool in the first 10 minutes? All right, slightly different question. Now we already know that this is talking about the change in the temperature of the coffee in the first 10 minutes. What's the 90 referring to?
The starting temperature.
That's starting temperature of the coffee in degrees, and we're adding to that a change in the temperature of the coffee in degrees. So we're taking degrees and adding degrees. That's good. Okay, you always want to be adding apples and apples and oranges and oranges. Our units are the same. So what does this total thing calculate? It's not just how many degrees did the coffee cool. It's something slightly different.
The temperature of the coffee after 10 minutes.
Yes. So this is the temperature of the coffee, not its change in the temperature, but its actual temperature of the coffee 10 minutes after room temperature, after setting at room temperature. Now, I bring that up because if a question says, hey, how much did the coffee temperature change? But a different question says, what's the temperature of the coffee? Those sound like they're asking the same thing. They're very related to each other, but they're not exactly the same thing. One is just talking about the change in the temperature, and the other is looking at that change relative to whatever the starting point was. Now, reasonable to assume coffee is going to be cooling. So after 10 minutes, the coffee should be less than 90 degrees, not more than 90 degrees. That means that this calculation, whatever that number happens to be, better be a negative number. If it's not, then something went wrong, because we would expect for the total change in the coffee's temperature to be negative because the temperature of the coffee is decreasing. All right, now again, so first off is just subtle distinctions between what question is being asked. Now let's actually talk about how you could use Desmos to get something more precise. So we have a formula here. It's -7 0.9 to the t dt, and Desmos will give us a good approximate value for that. So let's go to Desmos for this. Hold on, there we go. Oh, recall that Desmos has a built-in estimator of definite integrals. If it's under here under your functions, you click on miscellaneous, it's right there. We'll have our 0 to 10. Then you enter your function, which in this case is -7 0.9 to the t power dt, and that tells us that the coffee dropped in temperature by about 43 degrees over that first 10 minutes. It lost a lot of temperature in that first 10 minutes. Now, that would be answering the first question. We would need to have an approximation symbol in anything that we would represent, because we want to be clear that this is rounded off. This is not an exact calculation. It's just an approximate calculation, but pretty darn good. And if you wanted to get the second thing that we talked about, Desmos can handle that too, because we would do 90 plus that change. And so 90 taking away 43 is giving us the 46 that we're looking for. So again, Desmos can make it really easy on you if you're actually given a formula to work from. You do have to know how to convert the sentence in words into a definite integral. That's really the key element there. But as long as you know how to do that, then Desmos will do all the heavy lifting to get to an approximation. Now, just a little bit of forward looking. We would like to be able to do better than approximations sometimes. So right now, all of our techniques have been approximation techniques. what we're going to be talking about for the rest of the semester is, okay, great. Now, how do we get something more exact when we're evaluating a definite integral? Even if we interpret it the exact same way, we would like to get a more precise result and not just oh, it's around 44 degrees. So we would like to be able to say exactly how many degrees that it is. But again, for today, everything that you're going to be doing is still going to be in this approximation zone. So the big things that we're practicing today is, do you know the units of your definite integral and can you interpret it? Meaning, can you go from an integral statement to a sentence, and can you go from a sentence to an integral statement? And then applying those interpretations if you are given a graph, applying those interpretations if you're given a function, and applying those interpretations if you're given a table. So practicing those evaluation skills that we've had in previous sections, just adding on units into the mix. All right, it is 2:45, so you should have access to the problem list now.